In this video, we are going to study the sides of right triangles and trigonometric ratios. Now, if you recall, a right triangle is a triangle with a 90-degree angle, and we symbolize that with a little box. So this would be our 90-degree angle. The side opposite the 90-degree angle is our hypotenuse. I'll abbreviate it HYP. And then we have on either side of the 90-degree angle, we have the right triangle legs. In the blue box, we define the trigonometric ratios. The first ratio is an abbreviation for the sine ratio, and you spell sine, S-I-N-E, but we abbreviate it S-I-N. And we would find that ratio by taking the opposite side of the angle and divide it by the hypotenuse. The next ratio is cosine. That's spelled C-O-S-I-N-E, but we abbreviate it C-O-S. We have the tangent ratio, but we abbreviate it T-A-N. And then we have the cosecant ratio, but we abbreviate it CSC. And then we have secant, which we abbreviate SEC. And then we have cotangent, which we abbreviate COT. In the first example, it says find the trig ratios for the two triangles below. So I'm going to label this as triangle A and triangle B. For triangle A, we got to find the sine of theta, cosine of theta, tangent of theta, cotangent of theta, secant theta, and cosecant theta. And we're going to do that for both triangles. Okay. For triangle A, the smaller triangle, if we're looking for the sine of the angle, if we look up in the blue shaded box, it says the sine of the angle, that ratio would be the opposite side over the hypotenuse. So since my angle is right here, my opposite side would be 3. And my hypotenuse is always the side opposite the right angle. So this would be my hypotenuse. And then, of course, the side that goes against the angle that's not the hypotenuse is the adjacent side. So when I'm looking for my sine of the angle, I'm looking for the opposite over the hypotenuse. So I'm going to list the sine as 3/5. The cosine is the adjacent over the hypotenuse, so that would be 4/5. The tangent is defined as the opposite over the adjacent, so that is going to be 3/4. The cotangent is defined as the adjacent over the opposite, so that will be 4/3. The secant is defined as a hypotenuse over the adjacent, so that's going to be 5/4. And then the cosecant is defined as the hypotenuse over the opposite. So that would be now we're going to do the same thing for triangle B. If this is our angle here, then this would be our opposite side, and this is our adjacent side. And of course, the side always opposite the right angle is the hypotenuse. So we're going to do the same thing for triangle B. But what we're going to find is that these ratios are the same, which is why we labeled the angle the same. So if you look at the sine for triangle B, the sine is defined as opposite over hypotenuse. So if I take the opposite, which is 30, over the hypotenuse, which is 50, that's 30 over 50, and when I reduce it, I get 3/5. So I'm going to find that I get all the same answers once I reduce it. So the cosine is defined as adjacent over hypotenuse. So that's going to give me 40 over 50. When I reduce it, it's 4/5. So all of these are going to have the same values when you go through and find them and reduce them. So that tells me that these two triangles are similar. In the next example, it says find the trig ratios for angles alpha and angle beta. So if you look at this triangle, we have the two legs of the triangle. We know their lengths are 5 and 3. However, we do not know the length of the hypotenuse. We can very easily figure it out using Pythagorean theorem. If I take 5 squared plus 3 squared, that will give me c squared. So the hypotenuse is going to end up being the square root of 34. Now, for each angle, we need to find all the trig ratios. So let's start with angle alpha. If I want to find sine of alpha, that means I'm looking at this angle right here in red. So that means this side of alpha is going to be the opposite side. This is going to be my adjacent side, and this would be my hypotenuse. The hypotenuse is always the side opposite my right angle. So when I want to find the sine of alpha, that's the opposite over the hypotenuse. Since the opposite is 3, the hypotenuse is the square root of 34, I'm going to get that the sine of alpha is 3 over the square root of 34. Cosine of alpha is adjacent over hypotenuse, so that's going to be 5 over the square root of 34. The secant of alpha is hypotenuse over adjacent, so that's going to be the square root of 34 over 5. Cosecant of alpha is going to be the hypotenuse over the opposite, so that's going to be the square root of 34 over 3. Then we have tangent of alpha. Tangent is opposite over adjacent, so that's going to be 3/5. And cotangent is adjacent over opposite, so that's going to be 5/3. So these are all of our trig ratios for the angle alpha. Now, when we're going to find it for beta, let me erase all the red here. Let me do beta in blue. Beta is this angle here. So when I look at beta, the opposite side now for beta is 5. And the adjacent side for beta is 3. And of course, the square root of 34 is still the length of the hypotenuse because the hypotenuse never changes. It's always the opposite side of the 90-degree angle. So when I find sine of beta, my adjacent and the opposite sides get flipped. Sine is opposite over hypotenuse, but now the opposite side is 5. So I'm going to do 5 over the square root of 34. Cosine of beta is adjacent over hypotenuse, so that's 3 over the square root of 34. Secant of beta is hypotenuse over adjacent, so that's the square root of 34 over 3. Then tangent of beta is opposite over adjacent. So opposite is 5 and adjacent is 3. Cotangent of beta, adjacent over opposite. So that's going to be 3/5. And lastly, we have cosecant. And cosecant is defined as hypotenuse over opposite. So that's going to be the square root of 34 over 5. So these are all the trig ratios for alpha and beta. So the reason why I wanted to go over this example with you is for you to understand that depending on what angle you're looking at, the adjacent and the opposite side could be different. So it's really important when you're looking at a triangle to first identify what angle it is that you're looking at before you start trying to find your ratios. In this example, it says sketch a triangle that has an acute angle theta, where theta is defined by using the cosecant ratio. It says cosecant of theta is equal to 11/5. Now, since cosecant of theta is defined as the hypotenuse over the opposite, then I know the hypotenuse needs to be 11 and the opposite side of theta needs to be 5. So if I sketch my triangle, here's my 90-degree angle, so this has to be 11. If I define this as theta, this angle here as theta, then the opposite side would have to be 5. So the only thing left I have to do to sketch the triangle is to find that third side or that other leg so I can completely draw this, which would be my adjacent side. So I can just use Pythagorean theorem to find this. So if I call this leg A and this leg B and the C, I would have A squared plus B squared is equal to C squared. So I would have A squared plus 25, because 5 squared is 25, is equal to 121, because C squared, that's 11 squared, which is 121. So I would get A squared is equal to 96. I would subtract 25 from both sides. And so A is going to be the square root of 96. Now, typically when we take the square root of both sides of an equation, we have to do plus or minus. But in this case, where we're talking about the length of something, we only have to worry about the positive square root because lengths are only positive. And then I can simplify this as 4 square roots of 6 because 96 can be written as 16 times 6. And I can pull the 16 outside of the square root by rewriting the square root of 16 as 4. So I know that side A now is 4 square roots of 6, and we've completed the drawing of the triangle. Now, once we have the complete picture of the triangle, if I wanted to, I could find the other trig ratios because I have all 3 sides of that triangle. Now, in this blue shaded box in your notes, we have the fundamental identities. And these are equations that represent ways to show the relationship between 2 different trig functions. And we can use these to find trig ratios in addition to looking at triangles. So, looking at the reciprocal identities, and we're going to be using this quite a bit in trig, so you're going to end up eventually memorizing these without even trying because we use them so much. This first one here says that the value of cosecant and sine are reciprocals. And if you look up here in our previous example, if you look at sine and you look at cosecant, they are reciprocals of each other. 3 over the square root of 34 and the square root of 34 over 3. The next one here says secant and cosine are reciprocals of each other. And if you look, here's cosine, 5 over the square root of 34, And here's secant, the square root of 34 over 5. Those are reciprocals of each other. And then this one here tells us that cotangent and tangent are reciprocals of each other. And if you see, looking at this example, we have found that tangent is 3/5 and cotangent is 5/3. This here is saying that if I take the value of sine and I take the value of cosine and I divide them, I'm going to get the value of tangent. So let's check it using our previous example. Our previous example shows that sine is 3 over the square root of 34. So we would have 3 over the square root of 34 over our value of cosine. Our value of cosine is 5 over the square root of 34. Now, when you have a fraction divided by a fraction, you flip the denominator and you change it to multiplication. So I have 3 over the square root of 34 times the square root of 34 over 5. I would get rid of the square root of 34, and I'm left with 3/5. And if you look, tangent of alpha is, in that example, 3/5. So it works. And then you can do the same thing if you would like to check it to convince yourself that it works. Cotangent is if you take the value of cosine and divide it by the value of sine. And then the Pythagorean identities are derived from the Pythagorean theorem. And I will prove these to you in a later section. Right now we don't have enough skills yet to do that. So later in the course, I'll prove to you that those are true when we get into the section on identities. So as of right now, I just want you to become familiar with these, and we'll prove them later. But again, you can use these to find other values if you don't have the triangle in front of you. So for example, I can use this equation to figure out the value of cosine if I know the value of sine. So again, using our previous example, if we come up here, it says the sine of alpha is 3 over the square root of 34. And I plug in 3 over the square root of 34 into that equation. I can solve that for cosine. So I would square 3 over the square root of 34, which would give me 9 over 34 plus cosine squared is equal to 1. I would have to subtract 9 over 34 from both sides. So that would give me cosine squared theta is equal to 25 over 34. I would take that 1 and make it 34 over 34. So I have a common denominator, and then subtract 9 over 34, which would give me 25 over 34. And then I would square root both sides to get cosine, because right now that's cosine squared, so I would have to square root both sides to get the value of cosine, which would give me 5 over the square root of 34. And if I look back up here, I can verify that cosine of alpha is 5 over the square root of 34, right here. So we can use these identities to find other values if I don't have the triangle in front of me. Okay, now for the next example, it says we need to use a calculator to evaluate these trig ratios. If you look at your calculator palette, we have 3 trig functions right on the face of your calculator. And it's 2 buttons above your 7, 8, and 9 button, or 2 rows above your 7, 8, and 9 button. It says sine, cosine, and tangent. Now, you have to make sure you are in the right mode. And this gets students all the time, and it also gets me. I have to force myself to remember to make sure I'm in the right mode on my calculator. If you look at the example that's in the notes, it says we need to find the tangent of 40 degrees. We're not in radians here. So I want to make sure that I go into mode first to make sure I'm in degree mode. So here's the mode button. Look to see where my arrow or my cursor is circling around that key. I'm going to hit mode. And I want to make sure mine's on the 1, 2, 3, the fourth row down. I don't know what row it is for yours, but you want to go here and see mine's highlighted on radians. So if I had tried to calculate this without changing modes, I would get an incorrect answer. So I want to arrow down and arrow over to degree and hit enter. And now it's going to stay in degree mode until I tell it to go into radian mode. So now I can hit the tangent button. If I'm trying to find tangent of 40 degrees, I'm going to hit the tangent button. It's going to come up with an open parentheses, and I'm going to put in 40. And then I'm going to close my parentheses. Now, some calculators, if you don't close the parentheses, it won't give you the right answer. So make sure you close the parentheses. I'm going to hit enter, and it's going to tell me that that ratio for tangent of 40 degrees is 0.839, and so on. We also can do this for cosine. Part B of this example says cosine of 20 degrees. I'm still in degree mode. It doesn't change out of degree mode until you go in and change it. So I know I'm still in degree mode, so I'm going to hit cosine, and then I'm going to put in 20 and close parentheses. So cosine of 20 is 0.93969, etc. Now, in the next example, this is where our fundamental identities are going to come in handy. It's asking us to find the cotangent of 14 degrees. However, there is no cotangent button on the calculator. So we have to do a little trick. Since I know, looking at my fundamental identities, that tangent and cotangent are reciprocals of each other, and I want to know what the value of cotangent is, but I only have a tangent button on my calculator, I can put in 1 over tangent of 14 degrees. And that will give me my value of cotangent, since cotangent and tangent are reciprocals. So I'm going to put in 1 divided by tangent of 14 degrees. And that's going to give me my value of cotangent, because tangent and cotangent are reciprocals. Now the same thing goes for the next example, part D. It says find the cosecant of 80 degrees. We do not have a cosecant button on our calculator, so I have to use the fact that I know that cosecant and sine are reciprocals. So I'm going to do the reciprocal of sine of 80 degrees to find the cosecant of 80 degrees. So the cosecant of 80 degrees is 1.0154, etc. So we can use our identity, our fundamental reciprocal identities, to find other values of functions using our calculator, even though we do not have a specific calculator button for cosecant, secant, or cotangent. Now I would do the same thing if I wanted to do this in radians. I would just make sure that I would go into radian mode on the calculator. So if I wanted to find the tangent of pi over 3 radians, I would just make sure that I'm in radian mode to do that. Okay, now let's talk about solving a right triangle. To solve a triangle in general, it's just a way of asking you to find the length of all the sides and the value of all the angles. And just a quick refresher from geometry class way back when in high school, you know that the sum of all the angles in a triangle need to add up to 180 degrees. Now that we've introduced you to radians, if your angles are in radian form, the equivalent of 180 degrees in radian form would be pi. So all my angles, if I'm looking at it in terms of radians, all my angles have to add up to pi. So looking at the first triangle, we'll call this triangle A, and we'll call this triangle B. We are going to solve the first triangle, A, which again means we're finding all the lengths of the sides, and we are going to find all the angles, all the values of the angles. Since the sum of the angles has to add to 180, I know that this angle here has to be 38 degrees, because I would take 180 minus 90 and then subtract 52 to see what's left. So I have found that angle, it's 38, so we know all the angles. But now we need to find the other two sides. We need to find the hypotenuse and the second leg. Now, if we had one of those two sides, we could use Pythagorean theorem to find the third side. However, we don't have enough information to use Pythagorean theorem. So what we're going to do is use our trig ratios instead to find the other two sides. Since I know that this angle here is 52, if I'm looking for the other leg, that would be the opposite side. So this would be the opposite side if I'm looking at the angle of 52. And then this would be the adjacent side if I'm looking at the angle labeled 52. So I know that the tangent of 52 degrees, that's my angle, 52 degrees, has to be, according to the definition of our trig ratios, opposite over adjacent. So since opposite is what we're looking for, I'm going to label that as x. And that's going to be over 35, because the length of my adjacent side is 35. So now we can solve this mini equation for x by cross multiplication. So I'm going to get x is 35 times whatever the tangent of 52 degrees is. So I want to make sure that my calculator is in degree mode. So hit your mode button and make sure that it's highlighted on degree. And then what we can do is we can take the tangent of 52 and then take that answer and multiply it by 35. And we'll find that the side x, which is our opposite side that we have labeled right now because we're looking at the angle of 52. That side, if we round it to two places, would be 44.80. So this side right here, let me erase it now because we have it. This is 44.80. Now we have two legs and we're missing the hypotenuse. So from here, if we want, we could use Pythagorean theorem, but since we are trying to practice the new stuff, which is our trig ratios, let's go ahead and use trig ratios to solve for that last side. Now that last side is the hypotenuse. If I look at the angle 52, I have the adjacent side, which is 35, and the hypotenuse is what I'm looking for. So I can find the cosine of 52 degrees, that's adjacent over hypotenuse. So that's 35 over, I'll call it h for hypotenuse. And we can solve for h using cross multiplication. So I would have h times cosine of 52 degrees is equal to 35. And divide both sides by cosine of 52. So 35 divided by cosine of 52 degrees would be my value of h. So in the calculator, I'm going to take 35 and divide that by the cosine of 52 degrees. And I'm going to get that the hypotenuse rounded to two places would be 56.85. So this side here, the hypotenuse, has a length of 56.85. So now we found the lengths of all three sides, and we found all the angles. So triangle A is officially solved. Okay, now let's solve triangle B. It looks like in triangle B we have the hypotenuse because it's the length of the side that's opposite the right angle. And we're given one other angle, which is pi over 8. The total of the angles should add to be pi, which would be equivalent to 180 degrees. So in order to find that last angle, I need to take pi and subtract pi over 2, which is equivalent to the 90-degree angle, and then subtract pi over 8 and figure out what that value is. So in order to do this, I need to find a common denominator. So I'll use 8. So I'll make this 8 pi over 8 minus 4 pi over 8 minus pi over 8. So when I take 8 minus 4 minus 1 pi, that gives me 3 pi over 8. So that's this missing angle right here in radians. Now let's find the other two sides using that we know what our trig ratios are. If I look at this angle right here, pi over 8, if I use that along with the hypotenuse, this side here would be my opposite side. And opposite over hypotenuse is my sine. So I could take the sine of pi over 8, and that would be equal to my opposite over hypotenuse. Since we're looking for the opposite, I'll call that x, and the hypotenuse is 33.5. Now I'm going to cross multiply to solve for x. So I'm going to have x is equal to 33.5 times sine of pi over 8. So that, when I put that in the calculator, that will give me my length of the opposite side when we're looking at the angle pi over 8. Now, because of the previous example, I know that I'm in degree mode. So I have to go back into my mode on my calculator. Since this is in radians, I want to change my mode to radians. This is what usually gets people, is that they forget to switch modes and then they don't understand why their answer doesn't make sense. I do it as well. You're not the only one that it's going to happen to. I do it all the time myself. Okay, so now we're in radians. So I'm going to take 33.5 and multiply it by the sine. And then in parentheses, I'm going to use my pi button, which is above my division sign. I'm going to find the sine of pi over 8, enter, and I'm going to get that value is, if we round to two places, 12.82. So the length of that opposite side here is 12.82. Now to find the last leg, I could either use Pythagorean theorem, which we have enough information to do that. It's totally fine to do that. But for this video, I'm going to practice our trig ratios because this is what's new. So we're looking for our adjacent side now. Because we're looking at the angle pi over 8, the missing length would be the adjacent side. So I'm going to use cosine of pi over 8 because cosine is adjacent over hypotenuse. So my adjacent side would be x. That's the side we're looking for. And over the hypotenuse would be 33.5. So I'm going to cross multiply to solve for x. I know I'm in radian mode because I just did that sine of pi over 8. So I'm going to take 33.5 and multiply it by the cosine of pi over 8. That is going to give me an answer, when I round it to two places, 30.95. So this side, the opposite side, would be 30.95. Now, you can always use Pythagorean theorem to go back and check your answer. If I take 30.95 and square it, and then I add it to 12.82 and square it, and then that should be equivalent to 33.5 squared. Now, if you check it after you rounded it, it might come out slightly off because we rounded those values, but it should be really close where you could tell that you've got the right answer. Now, in this shaded blue chart at the bottom of the page, it says special values of the trig functions. These are just values that are very common and that are going to be used quite a bit, especially when we look at the unit circle later on in the course. these will be derived for you when we go and derive the unit circle. So for right now, I'm not going to prove these to you. This will be another IOU. And right now I just want you to become familiar with these special trig values. So the way you want to read this chart is we have two columns here, depending on if you're looking at radians or degrees. If you're looking at degrees, you look at the first column here. And let's say I ask you to find the tangent of 45 degrees. So I look at tangent, and I look at 45 degrees, and where they cross, it would give me that answer of 1. If I'm looking at radians, let's say I ask you to find the secant of pi over 3, then we look at this column here, and we look at this column here, and I say the secant of pi over 3, so I look to see where those cross, and that would be 2. So for right now, I just want you to become familiar with these values in this table, and then later on in the course, I'm going to actually show you where these come from and how they were derived using our previous knowledge of trig and your previous knowledge of geometry. Now for the cofunction identities, this is another way of showing the relationship between some of the trig functions. So there is a relationship between cosine and sine. There is a relationship between tangent and cotangent. And there is a relationship between secant and cosecant. And these cofunction identities tell us how they are related. These cofunction identities tells us that the value of the trig function of the angle, in this case specifically t, equals the value of the cofunction of the complement of the angle. Complementary angles are angles that add up to 90. So what this is telling us, with all those fancy words, what it comes down to is this right here, for example, tells us that the cosine of, say, 30 degrees will be exactly the same as the sine of 60 degrees because 30 and 60 add to 90. Those two values of those functions are going to be the same. So another example might be if we look at the relationship between tangent and cotangent. Tangent of, say, 25 degrees is going to be the same as the cotangent of 65 degrees because 25 and 65 are complementary. They add up to 90. And then this one here tells us the same thing about secant and cosecant. I could say the secant of 1 degree is going to give me the same value as cosecant of 89 degrees because 1 and 89 add to 90. So if I have complementary angles and I take the cosine of one of those angles and the sine of the other, those are going to be the same value. And that's what these cofunction identities are telling us. It's telling us another way we can relate these trig functions.